Good morning, class. We're going to review Bayes' theorem. So I hope you have the lecture example that we're going to discuss in front of you. I sent it to you by email. If you don't, what you need to do is pause the video so that you can see this frame, copy out this problem statement, and then we'll, because I have to have the whiteboard, and then we'll resume our conversation. So for those of you who you need to stop the video now. Okay, let's solve this problem by two different ways because they will improve your understanding if you see both solutions and see how to reconcile the two solutions. Let's begin with an intuitive solution, thought experiment. Okay, so suppose the entire population is 1 million. That's how we start. It can be any large number. Okay, now how do we justify that assumption? We can't until the very end of the calculation, and then we'll see whatever this number happens to be. It can be any large number, 10 million, 100,000. It washes out at the end of the calculation. It's very unusual in mathematics that you can make up a number like that that doesn't appear in the problem. Okay. So, what is the infection rate? That appears at the very bottom, well, near the bottom of the problem statement. It says only 0.1% of the population has TB. So, let's make a table here. Has TB, doesn't have TB. So 0.1%, you multiply by 0.001, of course. And that's 1,000. A tenth of a percent of 1 million is 1,000. And so it doesn't have TB. 1,000, 1 million minus 1,000 is 999,000. Okay, so now let's consider how many of these would test positive. Okay, so the problem says that if a patient has TB, he or she will be correctly diagnosed with probability 90%. So 0.9 times 1,000 is 900. Okay, now if a patient, so what we do is we imagine that all million, this is a very strange thing to do. It'd be very nice if we could do it in the present day. but we imagine that every single person in the population gets the test. Man, wouldn't that be great if we could test everybody for coronavirus? We'd be back to school in a couple of weeks. All right, so if a patient doesn't have TB, there's a 1% chance that he or she will be diagnosed as having TB. So 1% of this number is, so we shift the decimal point 2 places, so it's 9,990. So of the million people in the population, how many would test positive for TB? This number plus this number. So that sum is 10,890. Okay, so the probability that the patient has TB given that he tests positive for TB is, so this many patients would test positive, but only this many really have TB. So that number is 0.08264. About an 8% chance. Now, that answer is counterintuitive. Think about it for a minute. It seems to be a good test. For patients who are infected, the test is accurate 90% of the time. For patients who don't have TB, it's accurate 99% of the time. But we have this strange answer that if a patient tests positive, there's only an 8% chance that the patient really has TB. So it's the difference between P of F given E and P of E given F. Remember, we spent a lot of time discussing this. Okay, so that's the first solution. Let's erase this now and just record the essential calculation, and then we'll, so that we'll have it for comparison. So, first solution, it turned out to be 900 over 900 plus 9,900, I believe. Maybe there's another 9 there. So that's right. So that's 0.0826. Okay, here's the Bayes formula solution. So we need to define events E and F so that the answer to the problem is the probability of F given E. So what we're given in the problem statement is the patient tests positive for TB. patient really has TB. Okay, so let's write out Bayes' formula. It'd be a good idea, by the way, to review your class notes. Remember we discussed diagnosing FIV in cats earlier, so if you go back in your class notes and look at that example, that would be a good thing to do. Okay. All right, so we have these two conditional probabilities here. What's this? This is the probability that, let's see, the patient tests positive for TB given that he has TB. So we look in the problem, and that's 0.9, 90%. This is the incidence of TB in the population. So if we choose a patient random from the population, the probability that the patient has TB is 0.1%. So that's 0.01. As an aside, we really wish we knew what this number was for the coronavirus. It would make planning much easier. We don't want to be quarantining you longer than we have to, but we don't because of limited testing. So at any rate, continuing, this term is identical to this one. Now, if you remember, if you know the probability of an event, to get the probability of the complement, you subtract from 1. For instance, if the probability it's going to rain today is 20%, probability it's not is 80%, 100 minus 20. Okay, so this is going to be 1 minus 0.001, so that'll be 0.999. What about this one? What's the probability of a false diagnosis? So if the patient does not have TB, he will be falsely diagnosed as having TB with probability 1% chance, probability 0.01. Okay, so 0.9 times 0.001 is this, 0.009. Here it is again. 0.001 times 0.999, shift the decimal point.